Hello everyone, Sharanu Sharanarthigalu. Welcome to Sri Basava Public School, Elkal. We have started that already the new chapter in the physics, that name is Force and Laws of Motion. In the previous class we have studied Newton's second law of motion. Then we have studied that mathematical formulation of second law of motion, third law of motion, and along with we have studied their good examples of third law of motion. So today, my dear students, we will discuss conservation of momentum. The law of conservation of momentum states that the sum of momenta of two objects before collision is equal to sum of momenta after collision, provided there is no unbalanced forces acting on them. So here I will say the definition of momentum and here unbalanced force. So momentum means here we have already learned in the previous class. The momentum of a body is the product of its mass and velocity, correct? Okay. So formula of momentum is equal to mass into velocity, that is P is equal to m into v. So P is nothing but here momentum, m is nothing but mass of an object, so v is nothing but velocity. So clear? What is the SI unit of momentum here? The SI unit of momentum is kg meter per second. Okay. So now here you studied this point in the previous class. And what is the unbalanced force? If two forces act on a body in opposite direction, already you have studied, and if one force is greater than the other. So here we are using no unbalanced force acting on them. So let's begin once again the definition of what is the law of conservation of momentum. The sum of momenta of two objects before collision, before dashing is equal. Is equal are there? Equal to. Next, the sum of the momenta after the collision, provided there is no unbalanced forces acting on them. So we can understanding by the experimentally. Okay, so I will send. This means that the total momentum of the two object is unchanged or conserved by collision. See, when these two balls collide with each other or colliding, so after colliding, after dashing, they will move in the same direction in the opposite. Okay, two object is unchanged or conserved by collision. So you can see here we are taken that two balls, we named that A and B, and we can write on that MA and MB. MA means what here? Mass of ball A. MB means mass of ball B. And you have written in the before collision UA and UB. So these are the initial velocity of ball A and the initial velocity of ball B. So these are the two balls are there. We will do one activity. If two balls A and B of masses MA and MB are traveling in a straight line, they are traveling, observe the arrow mark, with the initial velocity UA and UB. And if UA is greater than UB, what it happen? The two balls will collide with each other, because the initial velocity of A ball is greater than the UB, then the movement will be changes in their body and dashing or colliding with each other. So during collision at a time t, ball A exerts a force, that is FAB. When the force is exerted by A on the ball B, so we can write it FAB. So FAB means what here? The force of A exerted on ball B. And suppose ball B exert a force that is FBA on ball A. So is it change their velocity? Yes, definitely change the velocity. If VA and VB are the velocity of balls A and B after the collision, we are seeing that before collision and after collision, what it happens in the momentum of these two balls. So before collision, the balls are moving in a straight line. If any between the two balls, anyone having the more force, so it can be changes their momenta. So this is the before and after the collision. We can observe that initial velocity and the final velocity. Here after collision we can get it. So those are the VA and VB. These are the final velocities. Okay. The momenta of ball A before and after the collision are MA UA and MA VA. And the momenta of ball B before and after the collision are MB UB and MB VB. So here I am telling that before collision of ball A, that is MA UA, and after the collision of ball A, MA VA. Then the momenta of ball B before is MB UB and after collision MB VB. Is it clear, my dear students? Are you understanding slowly? Okay, fine. Next you see change in momentum of ball A during collision. So now the changed. So final velocity minus initial velocity according to the equation of acceleration, you may plan here. Change in momentum of ball A during collision. So we may write it MA VA minus MA UA. So which one is the common factor here? So afterward you can take out. So rate of change of momentum of ball A. So in the bracket FAB is equal to MA is the common factor in the first during collision. MA you take out, in the bracket you may write it to VA minus UA divided by T. This is the rate of change of momentum of ball A. Now ball B is there. Change in momentum of ball B during collision is equal to MB VB minus MB UB. Now change here, rate of change of momentum of ball B in the bracket FBA is BA bracket close now is equal to common factor of in this equation MB. So you may write it in the bracket VB minus UB divided by T. So we have studied that before collision and after collision. Now you can apply Newton's third law of the motion after collision. So these are equal and opposite moment we can see in the balls. According to the Newton's third law of motion, the force FAB exerted by ball A on ball B is equal and opposite to the force FBA exerted by ball B on ball A. So this is we already know that every action always equal and opposite direction according to the Newton's third law. Therefore we may writing FAB is equal to minus FBA. So FAB means what here? A ball is exerted force on the B and B ball is exerted on the A. That time we are writing minus F. So now you can put the values here. FA. Okay. So FAB means what here? MA. Common factor, already we know that. Here in the above equation we found that FAB is equal to MA in the bracket VA minus UA divided by T. So already we found that FBA here, that is MB minus, you write it MB in the bracket VB minus UB divided by T. So now you can change the value here, multiple this one MA to the in the bracket of VA minus UA, and minus MB is multiple to the VB minus UB. Here TT are cancelled out, and now we can write it to MA VA minus MA UA is equal to minus MB VB plus MB UB. So now we can add, these are the minus, put values in the different way, minus MA UA minus MA UA is equal to minus MA VA minus MA MB VB. So we are making into separate, that is MA UA plus MB UB is equal to MA UA plus MB VB. So here MA UA, it shows that before collision and A ball, and in the MB UB it is also before collision. So after collision we can see that MA VA in the A ball and plus MB VB in the B ball. So this is momentum of the two balls before collision is equal to the momentum of the two balls after the collision. So thank you, students.
Let's start with the theory. Suppose there are two balls A and B. The ball A has mass MA, the ball B has mass MB. Both the balls are traveling along a straight line at initial velocities UA and UB, such that the ball A collides with ball B. During collision, the ball A exerts force on the ball B. Let's say the force is Fa, while the ball B exerts force on the ball A. Let's say Fb. Now, after collision, the two balls move with final velocity Va and Vb. In order to understand it more clearly, now let's formulate it. In the case of ball A, the ball A, which is moving with the initial velocity UA, has the initial momentum before collision, which is given by MA into UA. While the ball A moves with final velocity VA after the collision. So in this case, now the final momentum becomes MA into V of A. If we calculate the change in momentum, so it becomes MA VA minus MA U of A. If we take MA common, so it will become MA, and in bracket it will become VA minus U of A. According to second law of motion, the force is proportional to the rate of change of momentum. So we can say so that in the case of ball A, the force exerted was Fa, which is equals to the rate of change of momentum. The change of momentum, as we have already calculated in the above equation, that is MA, which is multiplied by the whole bracket, and inside the bracket there is VA minus U of A. It is divided by t because we are considering the rate of change of momentum. Now let's move on to the case of ball B. In the case of ball B, it is moving with the initial velocity u of b. So the initial momentum of this ball before the collision, it will become mb multiplied by u of b. Now after collision, the ball B moves with the final velocity Vb. So in this case, the final momentum now becomes mb into Vb. If we have to calculate the change in momentum, so it is given by mb Vb minus mb Ub. If we take mb common, so inside the bracket it will be Vb minus Ub. According to the same second law of motion, that is, the force is proportional to the rate of change of momentum, then the force exerted by the ball B is represented by Fb, which become equal to the change in momentum which can be seen from the above equation. The change in momentum, as we have already calculated, is equals to mb in bracket Vb minus Ub upon the time, that is t, because we are considering the rate of change of momentum. Now, during collision, we saw that the balls stick together. Here comes the Newton's third law of motion, and according to the third law of motion, for every action, there is an equal and opposite reaction. That is, if we apply this law in this particular situation, so we can say so that for every force, there is an equal and opposite force, which is Fa is equals to minus of F of B. From the two equations that we have already calculated the value of Fa and Fb, and let us substitute in this equation. So it will become Ma Va minus Ua upon T, which is equals to minus sign of Mb in bracket Vb minus Ub upon T. From both sides of the equation, the T gets cancelled out. Now open the bracket. If we open the bracket and consider the left hand side of the equation, so it will become MAVA minus MAUA, and in the RHS it will become minus MBVB plus MBUB. On rearranging both sides, we will get MAVA plus MBVB, and on the RHS side we will get MAUA plus MBUB. Considering the left hand side of the equation, MAVA is the final momentum of the ball A, while MBVB is the final momentum of the ball B. So if we add these two values, so it will give us the total momentum after the collision. Similarly, if we move on to the right hand side of the equation, so it gives us MAUA, which is the initial momentum of the ball A, MBUB, which is the initial momentum of the ball B. On adding the two terms, it gives us the total momentum before collision. So this is the law of conservation of momentum. Thus, from the above equation, we can say so that the total momentum of the system remains unchanged, or it remains conserved, provided no other external force acts on the system. Summarizing what we have studied till now, the first is that the conservation of momentum is used to describe the collisions between the objects. The second is that the total momentum of the system remains same, and this is called the law of conservation of momentum.
Thank you, my dear students. Sharanu Sharanarthigalu. Here the end of this chapter. That chapter name is Force and Laws of Motion. We will see in next class.